Okay, let's dive right into this. Welcome to today's Explainer. We're going to embark on a pretty fascinating journey today, looking at how matter literally transforms right before our eyes. Specifically, we're focusing on Lesson 2.2, Changes of State. We'll be looking a lot at water, a substance we use constantly but probably rarely stop to think about scientifically. We're going to explore the incredible ways it shifts from a solid to a liquid to a gas, and importantly, we'll learn exactly how scientists actually observe and measure these transformations in the lab. So here is our quick roadmap for the explainer. First up, the magic of changing states. Then we'll look at precision measurement for volume, followed by precision measurement for temperature. And finally, we'll wrap up with the heating water investigation. All right, part one, the magic of changing states. Everyday matter is constantly transforming around us, right? Often completely unnoticed. But to really understand this magic, we need a solid definition. A change of state is, well, exactly what it sounds like. It's the process where matter transforms between solid, liquid, and gas forms. And the absolute key driver behind all of these changes? Temperature. Whether you're looking at a solid ice cube melting on the kitchen counter or liquid water turning into invisible steam above a kettle, it is all completely dictated by how heat energy interacts with the substance. Think about the cycle of changing states, from solid ice to liquid water to invisible gas. It's an amazing continuous loop. You can trace the path of water simply depending on whether we add heat or take it away. If we leave solid ice in a warm place, it melts into liquid water. If we heat that water, it evaporates or boils into an invisible gas, water vapor or steam. But, the cycle goes the other way too. If that steam touches a cold surface, it condenses back into liquid. Pop that liquid in a freezer, and it freezes right back into solid ice. It's totally reversible. Let's break down these opposing actions a bit more, starting with melting versus freezing. These two processes are direct opposites. Melting happens when a solid turns into a liquid, right? And this happens at a very specific temperature, known as the melting point. On the flip side, freezing is when you lower the temperature and that liquid turns back into a solid. You really can't have one without the potential for the other. We actually see a very similar pairing with evaporation and condensation. Evaporation happens when water, say a puddle on the ground, gradually disappears as it changes into an invisible gas called water vapor. Interestingly, the warmer the water is, the quicker it evaporates. Condensation is the exact reverse of that. If that warm water vapor floats up and touches something cold, like a bathroom mirror after a shower, it instantly changes back into liquid water droplets. Now, while evaporation can happen slowly at all sorts of temperatures, boiling is a very specific, rapid event. Here are the key facts you need to know. Water boils when it is heated to exactly 100 degrees Celsius. This specific threshold, that's the boiling point. And at 100 degrees, the liquid rapidly changes into a gas or steam. It's a much more violent, energetic transformation than just your everyday evaporation. Moving on to Section 2, precision measurement of volume. Okay, so understanding the theory is really only half the battle. As scientists, we need to know how to accurately observe and record these changes. When measuring the volume of a liquid, you use a tool called a measuring cylinder. But here's the catch. Liquids don't just sit perfectly flat inside these cylinders. They actually form a slight curve at the very top. This curve is called the meniscus. It's a fun word, right? Meniscus? But if you don't know how to read it properly, your measurements will literally always be slightly off. What's really crucial here is the precise technique required for reading that measurement. You can't look down at the cylinder from above, and you definitely can't look up at it from below. You must bring your eye exactly level with the top of the liquid. From there, you measure the volume from the very bottom of the meniscus curve. It takes a little bit of practice, sure, but it is an absolutely fundamental lab skill for getting accurate data. Which brings us to Section 3, precision measurement of temperature. Once we know how much liquid we have, we usually need to know how hot or cold it is, especially when we're investigating changes of state. So let me ask you, how accurately can you read a thermometer? I mean, it seems simple enough, right? But just like the measuring cylinder, it requires a careful eye and a real understanding of how the tool actually works to avoid careless mistakes. When you use a standard lab thermometer, you're relying on the physical properties of the liquid sealed inside it. As the environment around the thermometer gets hotter, the heat transfers to the liquid inside. This causes the liquid to expand. And because it's trapped in this narrow glass tube, the only way it can expand is upwards, rising up the scale. Just like with volume, you read the temperature from the scale by making absolutely sure your eye is perfectly level with the top of the liquid inside the thermometer. And finally, Section 4, the heating water investigation.
All right, we have the theory down, and we have the measurement skills. Let's see how scientists put all this together in a real laboratory setup. Let's demystify the apparatus a bit. At the bottom, we have a Bunsen burner sitting on a heat-proof mat, ready to supply the heat energy. Above that is a tripod with a wire gauze to support a glass beaker full of water. Notice the clamp stand? It's securely holding the thermometer directly in the liquid. And, of course, our measuring cylinder and a stopwatch are right nearby to help with data collection.
Let's break down the scientific method step by step here. Step 1, you accurately measure 150 cubic centimeters of water using your measuring cylinder, remembering to read from the bottom of the meniscus. Step 2, you suspend the thermometer in the water using the clamp stand. Now, the crucial point is right here. You must suspend the thermometer so it measures the temperature of the water, not the hot glass at the bottom of the beaker. Step 3, record your starting temperature. And step 4, start the heat and record the temperature every single minute until the water boils vigorously. As you conduct the investigation, you obviously need a structured way to capture your findings. A simple table is perfect for this. You map the time in minutes, 0, 1, 2, 3, and so on, against the rising temperature in degrees Celsius. By laying out the data this way, you can clearly track how the addition of heat energy steadily drives the water toward its 100-degree boiling point. But hold on, before you ever light that Bunsen burner, we absolutely have to talk about safety. As the source material explicitly states, wear safety spectacles. Take care when handling hot water. Always stand up to carry out practical work. Standing up is key. It ensures that if there's an accidental spill of boiling water, you can quickly move out of the way. These protocols, they aren't just suggestions. They are the necessary foundation for being a safe and successful scientist. We've covered a lot of ground in this explainer today. We moved from the broad concepts of melting and boiling right down to the precise alignment of your eye on a meniscus. So I'll leave you with this provocative thought. Next time you boil a kettle for tea, don't just zone out waiting for the whistle. Can you identify every single change of state occurring? Can you imagine the rising liquid in a thermometer, tracking the precise temperature right up to that 100-degree boiling point? The world is literally a laboratory if you just know how to look at it. Thanks so much for joining me, and keep thinking like a scientist.